last lecture we had looked at some C programs and without really discussing the C syntax formally, tried to write some simple C programs and examine them and saw how they work. As I mentioned in the last class, starting today we will start discussing the C syntax and the various intricacies of the language from today. And today we'll first look at variables and types. So we have already used several variables in the programs that we have written so far, but there are restrictions on what the variable names can be. So far we have been using simple names like A, B, C, I and J, but actually the variable names can be pretty much as long as we like. But the restriction on the variable name is that it can only contain letters, lower or uppercase, that is A to Z, or numerals 0 to 9, or the special underscore character. It cannot contain any other character on the keyboard. In addition, the variable name cannot start with a numeral, that is, it cannot start with a digit from 0 to 9. So let's see some examples of valid and invalid variable names. Here are some invalid variable names: 3x, f bracket n, f bracket n minus 1. They are all invalid or illegal variable names. 3x is illegal because it starts with the numeral 3. Fn is illegal because of these parenthesis characters, the bracket characters. This one is also illegal because it has the bracket characters in it as well as the minus sign. Note that the minus sign is different from the underscore character. Here are some valid variable names. Instead of 3x, we could have called it x3. Here is an example where the variable name contains an underscore character, f underscore n or fn underscore 1. So this is the restriction imposed by the language on what the variable names can be. But also when we are writing programs, as I have said earlier also, we must make sure that our programs are readable so that they can be later understood by ourselves and by other people who are reading the program. And one very important aspect of program readability is that we should use descriptive variable names. That is, the variable names themselves should suggest what the purpose of the variable is. Okay, here are some more constraints on what the variable names cannot be. C has certain what are known as keywords or reserved words which cannot be used as variable names because these words have special meanings. We have already seen examples of these keywords. They have appeared in our programs. Int, if you recall, is a type integer, and so that's a keyword. It cannot be used as a variable name. What that means is that we can't have a variable called int. And similarly, we saw that while, if, else, etc. were special words that we use in our programs, so they can't be used as variable names either. But any other there are a whole lot of other keywords as well. But other than the keywords, any combination of characters containing only alphabets, numerals and the underscore and not starting with a numeral could be a valid variable name. But let me emphasize again that we should choose our variable names carefully so that they represent the purpose of having that variable. Okay, let's now look at types. We have already encountered types in the programs that we have seen so far. We have only seen one type so far, which was the integer type represented by the keyword int. But there are other types also available in C, large number of them actually. So the types are necessary because our programs as well as the computer can deal with data of various kinds. Integers are just one example. It could deal with real numbers, it could deal with strings made up of characters and so on and so forth. And in general, the values of different types are stored differently on the computer internally. For example, integers and real numbers are stored very differently. We have already seen in an earlier lecture that integers are stored in their binary representation. We'll shortly see roughly how the real numbers are stored inside the computer, and you'll see that the way they are stored are very different. And as you can imagine, different types may have different operations defined on them. For example, for integers as well as for real numbers, we have the arithmetic operations defined like addition, subtraction and so on. But for some other types, some other operations may be defined which may not make sense for integers in general. Even similar operations on different types may be implemented differently internally by the computer. For example, addition is defined for both real numbers and integers, but because the representation of integers and real numbers is very different, the computer has to perform addition of integers very differently from the way it performs addition of two real numbers, and therefore the compiler needs to know the type of every variable or value that is being manipulated by the program. That is because it has to generate the right machine code to manipulate these values or the variables. So let's first discuss the integer types in C in more detail. We have already seen the type int, which can be used for storing integers, but as we'll shortly find out, C actually defines a number of flavors of the integer types with slightly different properties. So integers can be either unsigned or signed. What that means is that whether negative integers can be stored or not. So an unsigned integer variable cannot store the negative integer value, whereas a signed integer variable can store both positive as well as negative integer values. The integers can be of different sizes. These are the various sizes of integers in C: char, short, long, or the regular integer. We'll soon see what the different sizes mean and what is the practical implication of this. So let's first focus our attention on signed and unsigned integers. So if we prefix the word unsigned, unsigned incidentally is another keyword. It's a new keyword that we are introducing now. If we prefix this to an integer type, then that's again an integer type, but it indicates a type where only non-negative integers can be stored. That is either 0 or positive integers. And instead of unsigned, if you use the prefix signed or no prefix at all, that indicates that both negative and non-negative integers can be stored. So for example, unsigned int would denote an integer type which can store only non-negative integers. On the other hand, signed int or simply int would denote an integer type which can store both negative as well as non-negative integers. So here are the examples we just discussed. Signed int is the same as just int. Both negative and non-negative integers can be stored. Unsigned int, on the other hand, denotes an integer type that can only hold non-negative integers. So we cannot assign really a negative integer to a variable of type unsigned int. It will result in some kind of an error. Okay, and as I said, integers can also be of various sizes apart from being signed or unsigned. So the size of a type here really denotes the number of bits used to store the values of that particular type. If you recall from the earlier lecture, we had seen that the integers are stored internally in their binary form, and the number of bits available for storing the integer really determines what is the largest integer that can be stored in that particular type. So a type with a bigger size can store a larger range of integers. The different size integer types in C are char, short int, which can be used as just short, int, and long int. Long int is the same as just long. They are the integer types of various sizes in C. We'll discuss their sizes in a minute. And in addition, each of these can be signed or unsigned. So here is the list of all the integer types in C. We can have just a plain integer, which can be signed int or just int. We can have an unsigned integer, which we can write as unsigned int or just unsigned. We can have a long integer, which is written as long int or just long. An unsigned long integer, unsigned long int or just unsigned long. A short integer is written as short int or just short. An unsigned short integer is written as unsigned short int or just unsigned short. A signed character, which is written as signed char or just char. Don't really get misled by the fact that the name here is char instead of int. This is there for a specific reason which we'll discuss later on when we talk about representation of characters inside a computer, we'll see that the same type is actually used for representing characters also, but it's actually just another integer type. So we'll just think of it right now as an integer type. And the unsigned char type. So let's see what their sizes are and what the size has to do with the smallest and largest integer that can be stored in a variable of a certain type. So if you have a signed integer type with size n bits, then it can store integers from minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1, both inclusive. We'll just state that and not really show why that is true. On the other hand, if we are talking about an unsigned integer type, again of size n bits, then the largest integer that can be stored is 2 to the power n minus 1, and of course the smallest integer is 0. Remember that in an unsigned integer type you cannot store negative numbers. Now out of the different integer types of various sizes that we have seen so far, char, short, int and long, the C standard definition, the C language definition defines only the size of the char type, which is 8 bits, which is, if you recall, the same as 1 byte. A group of 8 bits is called a byte. And it does not define the sizes of the other types like short, int and long. And so the size of these types may vary from different computer to different computer, from one computer to another. So on one kind of a computer, the short may be 16 bits, on another it might be just 8 bits and so on. But what the language guarantees is that short is at least as big as char, int is at least as big as short, and long is at least as big as int. So on a typical PC, which is running Linux, which is the kind of machine that we are using in this course, these are the typical sizes of the various types. Char, as always, of course, is 8 bits. Remember that char is 8 bits on every machine. And on a PC with Linux, short is 16 bits or 2 bytes. Int and long are both 32 bits or 4 bytes. So on this particular machine, it doesn't really matter whether I declare a variable as int or long, because both are 32 bits. But remember, on a different machine, it might make a difference, because on a different machine, for example, int could be 32 bits and long could be 64 bits, or maybe int is 16 bits and long is 32 bits. So therefore, we have to use the correct type, choose the correct types of our variables depending on how large we think the value of that variable is likely to be. Now, since the sizes of these types can vary from system to system, there is a way for C programs to find out what is the size of a given type within the program itself, and that is done using the size of operator in C. So if, for example, if I use the expression size of int, then this will have the value 4 on a PC running Linux. So let me illustrate this with a small program. Okay, here is a small program which prints the sizes of various integer types. So note that this program has no input. It doesn't read any input from the user. It has just 4 printf statements, and each line prints the size of a particular type is so many bytes. So this %d, if you remember, would be replaced by the value of the parameter, which in this case would be size of char, which of course, as we know, is going to be 1 byte, and in this case it will be replaced by size of short, size of int, size of long, and so on. Note that the size of unsigned short is the same as short, and similarly the size of unsigned int is the same as the size of int, and so on. So we don't really need to find out the sizes of unsigned int and unsigned short separately. So let's compile this program and see what output it gives. Okay, so this confirms the fact that I just told you, that on this particular machine, this kind of a machine which is a PC running Linux, the char has size 1 byte. This, remember, will be true on every system. but on this system, short has size 2 bytes and int and long has size 4 bytes, which may be different on different systems. But remember that the guarantee we have from the C language is that the short will have size at least as much as char, int will have size at least as much as short, and long will have size at least as much as int. Okay, so let's now go back to another type that will be quite useful, and that is the types rather of real numbers. So we have been dealing only with integers in the programs that we have written so far, but as you can imagine, oftentimes we might need to deal with real numbers, especially when we want to do scientific computations. And as I said earlier, real numbers are represented very differently inside the computer from an integer. So a real number is really represented as a sign, whether the number is positive or negative, an exponent, which is some power of 2, and the mantissa or the fractional part of the integer. We don't really need to know the ideas behind this in great detail. The point that we're trying to make at this point in time is simply that the representation of integers is very different from that for real numbers, and the implication of this particular kind of representation is that real numbers can only be represented approximately. That is, we have only a finite number of bits to represent the mantissa or the fractional part of the real number, and so the accuracy is limited. On the other hand, the integers are stored absolutely precisely. But the difference is that while integer types have a relatively smaller range, so for example on the machine that we just saw, the size of integer type is 4 bytes, that is 32 bits. So that means that the largest integer that we can store in an int type would be 2 to the power 31 minus 1. The range of real numbers on the other hand is much larger, but the precision is restricted. Let's now look at the real number types that are available in C. There are two of them really. They are called float and double. The word float comes from the fact that the representation of real numbers that we just saw is called the floating point representation, and the word double comes from the fact that the double type has about twice the precision as that of the float type. So as I said, double has much more precision than the type float. But both have about the same range, that is the smallest and the largest real numbers that can be stored are about equal in both these types. The difference, remember, is in the precision. So the double type is typically used in scientific applications that require a high degree of precision. Let's now write a small program to illustrate the float type, and this program is to compute the area of a circle. Fairly simple program given the radius of the circle. So obviously we want to represent both the radius and the area of the circle by real numbers. So here is the program. Remember that hash include stdio.h will be present in pretty much all programs that we write. This just says that we are going to use some standard input and standard output libraries. Function in the standard IO library. So here are the variables that we are going to use. The variable radius will represent the radius of the circle that the user will input. The variable area will represent the computed area of the circle. Phi, of course, is the well-known mathematical constant, and we are using its value 3.1419. Of course, we could have used a more precise value for phi. So this program is quite simple. As you can see, we give the user a prompt to enter the radius, and then we have to read the radius from the user. Remember now that radius is a floating point variable or a float of type float, so we can't use scanf%d to read it. We'll still use scanf to read the value of radius, but instead of using %d, we'll use %f. And remember that in scanf, the variables have to be preceded by this ampersand. So once we know the value of the radius, the value of the area is very simple to compute. It's just pi r square or pi times radius, and then we are printing the output, which is area of the circle with radius so much is so much. So again, note that to print a floating point value or a real value, we are using %f instead of %d as we did for printing integers. And we are using the same printf statement actually to print two real values along with some text. So we have two %f in the format string, and the first %f will be replaced by the value of the radius, and the second %f will be replaced by the value of the area. So let's compile this program. Let's say we give the radius as 2.56, whatever that radius is, and it gives the correct area of the circle, which is 2.590755, which you can easily verify using a calculator. One more point I would like to make using the same program. Let's edit it again. And that is that in this program the variable pi is actually not really a variable in the sense that we will never want to change it once we have given it a value. Note that one more new thing that we have done in this program is that the variable has been initialized at the same time as when it has been declared. So this is the first time we have been doing this. So float pi is equal to 3.1419. So we can mix the initialization of a variable with the declaration. As I said, we really don't want to modify the value of pi ever in our program. So to indicate this, we could prefix this declaration by the keyword const. The keyword const tells the compiler that this variable is really a constant which should not be modified by the program. So it can only be initialized along with the declaration. It cannot be given a value later on. So the point of doing this is that if inadvertently by mistake our program happens to modify the value of such a variable, the compiler will give us an error message. Let's try to do that actually. Let's say 5.46. So as you'll see, this will give an error. Assignment of read-only variable pi. So this is not permitted. So that is the advantage of declaring variables as constants when we don't really want to ever modify their values. So this program will compile okay and will work the same as before. Here is the answer. Okay, so let's end this lecture with a problem for you. The problem is to compute the value of sin x given the value of x to a certain accuracy, let's say epsilon, which is also given. The accuracy basically means that the value of sin x must not, that is computed by the program, must not differ from the actual value of sin x by more than this amount. Now, the way you are going to do this is to use the Taylor expansion for sin x. Recall that sin of x is equal to x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial and so on. So you have to use this Taylor series to compute the value of sin x given the value of x, and since you have to compute it for the accuracy epsilon, that means that you should stop adding the terms of the sequence once the absolute difference between the last two terms that have been computed is less than epsilon. So let us say Tn is the last term that we have computed and Tn minus 1 was the term that we computed before that. Then when the difference is less than epsilon, the absolute difference is less than epsilon, then we can stop computing, and the sum that we have accumulated so far is the value of sin x to the desired accuracy. Also note that you can, in every iteration, when you want to compute some x to the power 2k plus 1 by 2k plus 1 factorial, You don't need to raise x again to the power 2k plus 1 and compute 2k plus 1 factorial. You can use the fact that in the previous iteration you computed the term x to the power 2k minus 1 divided by 2k minus 1 factorial. So given this value, to compute the next term, which is this, all you need to do is you need to multiply this by x square and divide by 2k times 2k plus 1. So you can see this will become x to the power 2k plus 1 into 2k plus 1 factorial, and that will give you the value of the next term. So try to solve this problem and write the C program for computing the value of sin x. We'll see the solution to this problem in the beginning of the next lecture.